The universe balances itself upon a blade so fine that even the smallest tremor can send reality plunging into chaos. Everywhere we look in the cosmos, this delicate dance between structure and collapse plays out in breathtaking fashion. When magnetic energy surges within a star, it lashes outward as a solar flare that rips through the cold vacuum of space. When a supergiant begins fusing iron, it sets off a chain reaction so violent that the star unravels into a cataclysmic hypernova. And when pressure mounts within the crust of a spinning magnetar, the sudden crack of a starquake releases torrents of gamma radiation into the void. These moments are not merely dramatic events. They are cosmic tipping points, instances where matter and energy, pressure and temperature, order and entropy reach their critical thresholds. The entire universe, from the tiniest atoms to the sprawling clusters of galaxies, exists in a state of suspended equilibrium, and even the smallest disruption can ripple outward into profound transformations. And yet, miraculously, stability often reasserts itself. Subatomic safety nets emerge, hidden forces rally, and matter finds new forms to cling to. Like a cosmic version of Jekyll restraining Hyde, the universe somehow keeps its most destructive impulses in check at least most of the time. Nowhere is this tightrope more evident than in neutron stars. These are not just the remnants of stellar collapse, they are physics pushed to its breaking point. Imagine a star the size of a city, yet heavier than our sun, spinning dozens or even hundreds of times every second. Its gravity is so intense that if you were to drop something from shoulder height, it would reach half the speed of light before hitting the surface. Mountains here rise only fractions of a millimeter before the crushing gravity flattens them again, and the deeper one ventures into this stellar corpse, the stranger things become. The layers grow denser, the forces fiercer, and the laws of physics more tenuous. Understanding what happens inside neutron stars is not just an astrophysical curiosity, it is a gateway to understanding matter, space, time, and the very fabric of existence itself. Neutron stars are the last stronghold before matter folds in on itself completely. They are nature's ultimate experiment in extremity, a place where the universe tests its own limits, balancing on the razor's edge between endurance and collapse. To truly grasp these bizarre objects, we must start with the one star we know best, our Sun. On the night of December 24th, 2024, as families on Earth immerse themselves in the warmth of celebration, a spacecraft named the Parker Solar Probe was dancing through peril, traveling at 200 kilometers per second. It came within 6 million kilometers of the solar surface, closer than any human-made object has ever dared. That distance might seem vast, but in astronomical terms, it is as if the Parker Solar Probe had dipped a fingertip into the flames of a bonfire. It entered the corona, the Sun's outermost layer, a ghostly halo of superheated plasma that launches violent coronal mass ejections into space. These ejections are the Sun's tempests, storms of ionized matter so powerful they can knock out satellites and power grids on Earth. Yet the corona is not the whole story. Below it lies the chromosphere, a thin layer of fiery gases at 5,000 degrees Celsius. Beneath that lies the photosphere, the layer we see from Earth, a boiling ocean of plasma where hot gases rise, cool, and sink again in a mesmerizing dance. But to unlock the mystery of why the Sun burns and what it tells us about neutron stars, we must travel further back, not through space, but through time to colonial India in the early 20th century. Amid political upheaval and calls for independence, a teenager named Meghnad Saha found himself expelled from school for his role in protests against British rule. That same young man would go on to become a leading astrophysicist. In 1923, he developed the Saha ionization equation, a breakthrough that allowed scientists to calculate the degree to which various elements in a star are ionized based on local temperature and pressure. This was more than just a formula. It was a new way to read the sun's inner workings. Ionization is the process by which electrons are stripped from atoms, turning ordinary gases into plasma, the fourth state of matter. Most of us learn in school about solids, liquids, and gases. Plasma is the realm beyond, an electrically charged soup of subatomic particles. The photosphere of the sun is partially ionized, a mixture of gas and plasma. But as we dive deeper, the plasma becomes dominant. By the time we reach the core, we have entered a realm of unimaginable pressure. The temperature soars to 15 million degrees Celsius, and the density reaches 150 grams per cubic centimeter, 8 times denser than gold. In this inferno, hydrogen atoms are smashed together with such force that they fuse into helium, releasing immense amounts of energy. Every second, 620 million tons of hydrogen vanish, and 616 million tons of helium take their place. The missing mass is converted into energy, sustaining the sun's radiant glow. But this energy takes a long time to escape. On average, photons created in the core will take 170,000 years to fight their way to the surface. The balance between the outward pressure of this energy and the inward pull of gravity is what keeps the sun stable. This balance is known as hydrostatic equilibrium. Physicists describe this equilibrium using the equation of state, a formula that connects pressure, temperature, and density. In the sun, this equation is well understood, but things become more complicated as stars evolve. As they run out of fuel, the balance begins to falter. Gravity pushes inward with no opposition, and the star contracts. What happens next depends on the star's mass. Smaller stars become white dwarfs, stabilized by electron degeneracy pressure, a quantum force arising from the Pauli exclusion principle, which states that no two electrons can occupy the same state. The electrons resist being squeezed too close together, generating a pressure that halts the collapse. This was the insight of Ralph Fowler, whose wartime injuries led him to pivot from ballistics to astrophysics. Fowler's work laid the foundation for understanding white dwarfs and later, neutron stars. One of the most iconic white dwarfs is Sirius B, the pup, a companion to the bright star Sirius. Though no larger than Earth, Sirius B is more massive than the Sun. Its matter is so tightly packed that a sugar cube of it would weigh as much as an elephant. Such density should cause collapse. Yet degeneracy pressure holds it at bay. But even this quantum pressure has limits. Subramanian Chandrasekhar, building on Fowler's work, showed that if a white dwarf exceeds 1.4 solar masses, degeneracy pressure will fail and collapse will resume. This is the Chandrasekhar limit, the tipping point beyond which a white dwarf becomes a neutron star. In these more massive remnants, gravity crushes protons and electrons together to form neutrons. These, too, resist compression, thanks to neutron degeneracy pressure, offering one final buffer against total collapse. But what happens beyond this point, and what secrets lie buried in the heart of these neutron stars? That is the mystery we will begin to unravel in the chapters ahead. To study these cosmic balancing acts is to look into the fundamental nature of reality. Stars may burn and explode, collapse and flare, but always they reveal something about the rules that govern everything. And as we turn our gaze inward to the strange and powerful world of neutron stars, we begin to grasp the staggering question, how far can we push the universe before it breaks? The collapse beyond light. The tipping points that give birth to neutron stars are not isolated eruptions of energy, but part of a long and interconnected history of ideas, calculations, and revolutionary insights. Among the trenches of the First World War and the debris of fallen empires, a quiet intellectual revolution was stirring. When a French battleship disappeared beneath the waves in the Dardanelles in the spring of 1915, the headlines spoke of defeat. But in a hospital far from the front lines, a wounded soldier named Ralph Fowler began a transformation that would shift the course of theoretical astrophysics. His injury, suffered during the chaos of Gallipoli, led him to a new life among fellow scientists, where conversations and wartime improvisations laid the foundation for a new understanding of collapsed stars. The same bullet that pierced his shoulder ended a military career and opened the door to one of the most influential collaborations in modern science. Out of these connections, Fowler's curiosity began to pivot toward the stars. And by the 1920s, Fowler's work on quantum gases laid the groundwork for understanding the peculiar behavior of electrons squeezed into tight corners of space. This concept degeneracy pressure explained how white dwarfs resisted collapse. But it also planted a deeper question. What if gravity grew too strong, too relentless, even for this strange new pressure to resist? This puzzle was taken up by a young Indian astrophysicist named Subramanian Chandrasekhar. At just 19, aboard a ship sailing from India to Cambridge, he calculated the theoretical limit beyond which a white dwarf would be unable to resist gravitational collapse. This number 1.4 times the mass of the Sun became known as the Chandrasekhar limit. It was not just a mathematical threshold, it was a cosmic guillotine. Chandrasekhar's insight was met with skepticism. The idea that there existed a fatal weight limit for stars ran counter to prevailing beliefs. Among the most vocal critics was Arthur Eddington, one of the most prominent astronomers of the time, who believed the concept absurd. But physics does not yield to opinion, and eventually, the community recognized the significance of the limit. What followed next was an explosion in our understanding of stellar death. Stars above the limit could not become white dwarfs. Instead, they would collapse further, pushing beyond the realm of electrons and into a denser, more mysterious regime where protons and electrons combine to form neutrons. This new form of stellar remnant was compact beyond imagination. A white dwarf may be as dense as 1 billion kilograms per cubic meter, but a neutron star reaches densities 100 million times greater. A single teaspoon of neutron star matter weighs more than Mount Everest. This compression is so extreme that gravity reshapes the structure of matter itself, forcing it to become something altogether alien. The very existence of these stars challenges our most fundamental understanding of nature. To find one of the first physical clues of such bizarre objects, we look to the night sky. The Crab Nebula, a tangled mass of glowing gas and dust, marks the site of a supernova that lit up the skies in the year 1054. Ancient astronomers in China recorded the appearance of a new star, so bright it could be seen in daylight. But what they did not know is that deep within the center of this stellar shroud remained the collapsed heart of the exploded star. The core had been compacted into a neutron star, not just any neutron star, but one that spun rapidly, sending beams of radiation into space like a celestial lighthouse. Such spinning neutron stars came to be known as pulsars. They revealed themselves by their rhythmic flashes of light, first detected by radio telescopes in the 1960s. At the heart of the Crab Nebula, one such pulsar spins 30 times every second. And this is not even the fastest. Some rotate hundreds of times per second, their rotation preserved from the original spin of the massive star that gave birth to them. Like an ice skater pulling in their arms, the star's collapse accelerates the spin. But it is not only angular momentum that intensifies. The magnetic fields of neutron stars are also compressed and concentrated, reaching strengths that defy imagination. One neutron star's magnetic field can be 100 billion times stronger than that of a typical fridge magnet. In such extreme fields, physics becomes unpredictable. These stars are not simply objects. They are laboratories of fundamental forces. Yet even within their stability lies a question of limits. For just as white dwarfs had a maximum mass, so too must neutron stars. This realization led to the concept of the Tolman-Oppenheimer-Volkoff limit, a theoretical upper mass bound for neutron stars. If this limit is breached, not even neutron degeneracy pressure can withstand gravity's relentless pull. The star must collapse further. And the only known outcome of such a collapse is the formation of a black hole, a place where gravity overwhelms all resistance and not even light can escape. Neutron stars, then, are the final checkpoint before the abyss. Yet their interiors remain a mystery. We cannot see inside them, and the pressures and densities involved are impossible to replicate on Earth. To understand them, astronomers must rely on indirect evidence timing the pulses of pulsars, measuring their masses, analyzing their cooling rates, and watching for minute variations in their signals. One particularly revealing discovery came from the Neutron Star Interior Composition Explorer, or NICER, a telescope mounted on the International Space Station. NICER's precision allowed astronomers to map the surface of a pulsar by observing the way its X-rays fluctuated. These maps hinted at mountains mere millimeters tall and gravitational fields that bent light so strongly. The far side of the star became visible. Such observations allowed astronomers to measure not only the size of neutron stars, but also to test different equations of state models that describe how matter behaves at such unthinkable pressures. But even among neutron stars, there are outliers. One in particular, known as J0740, puzzled scientists. Despite having more than twice the mass of the Sun, it was no smaller than other neutron stars of lesser mass. This contradicted expectations. In theory, more massive neutron stars should be more compact. Their gravity should squeeze them tighter. Yet J0740 defied this logic. Its size suggested either a misunderstanding of the equation of state or the presence of exotic matter within. Perhaps, deep in its core, the neutrons break down into their constituent quarks, or maybe even stranger particles, hyperons containing strange quarks, begin to emerge, creating a new state of matter. These questions highlight the frontier that neutron stars represent. They are not just remnants of stellar death. They are crucibles where the rules of physics are tested, stretched, and sometimes broken. To study them is to touch the edges of what is knowable. In these cosmic collisions and quiet pulses, we glimpse the universe in its most extreme form, and as we prepare to journey deeper into their interiors, we ask once more what hidden forces hold back the night. The architecture of collapse. Beneath the crust of a neutron star lies a territory so alien, so physically extreme, that every law of classical matter is rewritten. Just below its surface sits an atmosphere barely 10 centimeters thick, an envelope of hydrogen and helium glowing at temperatures near 2 million degrees Celsius. But this fragile veil is deceiving. What lies beneath is a fortress of incomprehensible pressure. Within moments of entering the crust, the atoms are stripped of their electrons, and the nuclei find themselves suspended in a sea of free-floating particles, packed so tightly that even light struggles to escape. It is here that electrons, neutrons, and protons begin to form patterns that defy earthly analogies, twisting and weaving into configurations born not of chemistry, but of nuclear geometry. This strange, dense frontier gives rise to one of the most exotic materials ever theorized, nuclear pasta. At such extreme densities, the forces between nucleons, protons, and neutrons begin to create structures as oddly familiar as they are entirely unprecedented, like culinary analogies forged in a quantum forge. These layers of matter contort into gnocchi, spaghetti, and lasagna-shaped formations. This isn't whimsy. These terms refer to real theoretical arrangements predicted by sophisticated computer simulations. Spherical clusters form bubbles resembling gnocchi. Flattened sheets echo the stretch of lasagna. Long filaments curve through space like strands of spaghetti. This pasta, however, is not dinner table fare. It may be the strongest material in the universe, 10 billion times stronger than steel. Though no laboratory on Earth can reproduce these pressures, indirect evidence for the presence of nuclear pasta is mounting. The way neutron stars radiate heat, their spin-down rates, and sudden glitches in their rotation hint at structural rearrangements deep within. The rigidity of these pasta phases may even explain why neutron stars occasionally shudder in starquakes, a breaking of their internal architecture that releases bursts of radiation detectable across the cosmos. As we descend deeper, past the final folds of pasta, we encounter a domain where known matter begins to unravel. Neutrons, themselves once thought to be indivisible within stars, may begin to decay into their constituent parts. This realm remains hypothetical, but scientists believe that in the most massive neutron stars, pressure could become so great that even the neutrons lose their individual identities, dissolving into a fluid of quarks. Quarks are the fundamental particles that combine in threes to make up protons and neutrons. There are 6 known types: up, down, strange, charm, bottom, and top inside neutron stars. It is thought that only up and down quarks are typically present, but in extreme cores, strange quarks could emerge. This transformation yields what physicists refer to as quark matter, or more specifically, a quark-gluon plasma. In this state, the very building blocks of protons and neutrons slosh together in a sea of liberated particles, reminiscent of the conditions that existed in the first milliseconds after the Big Bang. These core regions would essentially host microcosmic echoes of the universe's earliest moment, a memory preserved in the heart of a dying star. But with this radical internal change comes an external paradox. If a neutron star becomes a quark star, an object made entirely of quark matter, then its density should increase further. This would, by gravitational logic, result in a smaller radius for more massive stars. Yet, observations like those of J0740 contradict this, implying that either quark matter behaves differently under pressure than expected, or that an entirely different form of matter exists at these depths. One such contender is dark matter. Though still elusive, dark matter is thought to comprise most of the universe's mass, exerting gravitational influence without emitting light. Some theorists propose that neutron stars, as they sweep through the galaxy, may scoop up dark matter, which then settles into their cores. If this dark matter interacts with itself or with baryonic matter, it could exert additional pressure or resist collapse in ways traditional models do not account for. This inclusion might help explain anomalously large neutron stars and open a new avenue for understanding both neutron stars and the universe's missing mass. Another theory gaining traction hinges not on exotic particles, but on quantum mechanics itself. Subatomic particles are defined not only by their mass and charge, but also by a quantum property called spin. Fermions, like protons and neutrons, have half-integer spin. And obey the Pauli exclusion principle, no two identical fermions can occupy the same quantum state simultaneously. This rule underpins degeneracy pressure. But bosons, particles with whole number spin, can share quantum states freely. If, under extreme conditions, fermions pair up to behave as composite bosons, they can collapse into a Bose-Einstein condensate, a state of matter where all particles move in concert as a single quantum entity. This possibility, though speculative, has profound implications. If the core of a neutron star transitions into a Bose-Einstein condensate, it may explain how these stars resist collapse even when exceeding conventional mass limits. It also reintroduces the name of Satyendra Nath Bose, the Indian physicist whose collaboration with Albert Einstein led to this prediction a century ago. In this way, the theoretical scaffolding of neutron stars ties back not only to astronomical observation, but to the deepest philosophical insights of quantum theory. Yet these stars remain mysterious partly because we cannot peel them open. We must rely on their emissions, on indirect measurements, and on the precise timing of the radiation they pulse into space. When two neutron stars collide, as happened in the event named GW 170817, we catch a rare glimpse into their interiors. The gravitational waves released carry information about their composition, while the light that follows from X-rays to gamma rays to visible light tells us about the debris. It is from these collisions that heavy elements like gold and platinum are forged. In a single explosion, the universe disperses its rarest treasures. All of this underscores a simple truth. Neutron stars are not merely remnants. They are living records of cosmic history, laboratories of extremes, and perhaps keys to unlocking fundamental truths about matter, gravity, and the evolution of the universe. They show us that at the edge of collapse, the universe invents new rules to hold itself together. The final barrier before the abyss. There is a boundary in the cosmos beyond which no force can resist collapse. If neutron stars are the last bastions against gravitational annihilation, then what happens when even they are pushed too far to understand this final tipping point? We must turn our gaze toward the darkest heart of astrophysics, where neutron stars can no longer hold their shape and instead fall into the abyss of black holes. But to reach that threshold, we must first examine how neutron stars walk their own perilous edge. The concept of a maximum mass for neutron stars, the Tolman-Oppenheimer-Volkoff limit, emerged in the early 20th century from minds struggling to quantify this final cosmic checkpoint. Early calculations placed this limit below the mass of the Sun, but modern refinements have pushed it closer to 2.2 solar masses, perhaps even higher. Anything beyond this and the neutron degeneracy pressure collapses like a scaffold torn from its foundation. The star succumbs to gravity in full, vanishing behind an event horizon from which no light can return. This transformation is not merely a continuation of stellar death, it is a redefinition of existence, where mass bends space-time so severely that even time itself seems to halt. But before crossing that threshold, neutron stars show signs of resistance. Some rotate at incredible speeds, and this spin helps counteract gravity. These millisecond pulsars, as they are called, generate centrifugal force that effectively adds structural support. The fastest spin measured so far exceeds 700 rotations per second, like a figure skater spinning faster as they draw their arms inward. These pulsars use angular momentum to delay collapse, but even spin has its limits. When accretion from a binary companion increases the mass of a neutron star too far, not even rapid rotation can forestall doom. The best evidence for the final mass limit came not from theory, but from observation. In 2017, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal labeled GW170817. It came from the merger of two neutron stars, each roughly 1.4 times the mass of the Sun. When they collided, they did not immediately form a black hole. Instead, they produced a transient hypermassive neutron star that survived for mere moments before collapsing. The gravitational waves and the accompanying light burst allowed astronomers to narrow down the Tolman-Oppenheimer-Volkoff limit with greater precision. They now believe it lies between 2.1 and 2.3 solar masses. What happens when this limit is breached is astonishing. The neutron star, already more massive than the Sun and compressed into a sphere the size of a city, implodes. In a fraction of a second, it becomes a black hole. Its core contracts infinitely, forming a singularity, an object of infinite density and zero volume. Around this singularity, space itself is so warped that not even light can escape. The surface of no return is called the event horizon. Inside it, all paths lead inward. No message, no matter, no memory can pass outward again. And yet, this is where theory begins to fracture. General relativity, the framework that describes gravity, predicts this collapse with ruthless certainty, but quantum mechanics, the law book of the small, cannot accept infinities. According to quantum theory, singularities are mathematical monsters, signs that something in our understanding has gone wrong. This tension between the largest and smallest theories in physics fuels the search for quantum gravity, a unified theory that can describe what happens inside black holes. Neutron stars, teetering just above this brink, offer our best hope of finding that theory. Because their interiors reach conditions nearly as extreme as black holes just shy of total collapse, they represent nature's laboratory for testing new physics. If we can understand what matter does at these pressures, we might be able to avoid the infinities that plague singularities. Some theories propose that black holes are not singularities at all, but instead contain quark matter or even more exotic states. Others suggest that the cores of collapsing neutron stars might bounce, forming structures that mimic black holes but never fully become them. There are also quantum theories that challenge our assumptions about event horizons. Some posit that the intense information content of black holes results in firewalls, hypothetical regions of searing energy that would destroy anything falling in. Others suggest that quantum entanglement might allow information to leak back out, subtly encoded in Hawking radiation. But none of these ideas have been confirmed. They remain mathematical whispers, waiting for neutron stars and their death throes to speak the truth. The need for better understanding became urgent with the discovery of the most massive neutron star ever recorded, PSR J0952-0607. Weighing in at 2.35 solar masses, it appears to defy the supposed maximum limit. How can it exist? One answer may lie in its rapid spin, which could temporarily stave off collapse. Another possibility is that our equations of state the relationship between pressure, temperature, and density are still incomplete. If the matter inside neutron stars behaves differently than expected, perhaps they can support more mass. Some models now suggest that neutron stars might transform into entirely new classes of objects before collapsing into black holes. Among these hypothetical stars are quark stars, where matter exists not as neutrons, but as free-floating quarks. Others propose gravastars, where spacetime itself undergoes a phase change, creating a stable vacuum shell that halts collapse. These ideas are speculative but tantalizing, offering new ways to think about gravity and the limits of matter. Even more exotic are ideas linking neutron star interiors to dark energy, the mysterious force accelerating the expansion of the universe. If a form of dark energy exists inside neutron stars, it could produce repulsive pressure that helps resist collapse. This would not only explain unusually massive neutron stars, but also provide a direct connection between the tiniest and largest forces in the cosmos. And yet, all these questions return to a single point: what lies within. Neutron stars, by their very nature, hide their truths beneath layers of mystery. Their surfaces are calm, their pulses precise. But beneath that stillness lies the potential for transformation more violent and fundamental than any explosion. Their collapse is not just an ending, it is a threshold into the unknown. Stars that refuse to die. To follow the story of neutron stars to its end is to chase a paradox: how something so small can contain such immensity, and how something so still can harbor such violent potential. As we look deeper into the strange physics of these compact remnants, we find that they are not the end of stellar life, but rather a crucible for new beginnings. Their collapse challenges our best theories, but their very existence offers something extraordinary: a window into the unification of the laws of the universe. Perhaps no mystery better captures this contradiction than the case of neutron stars that are colder than expected. In the summer of 2024, a team of astronomers led by Alessio Marino at the Institute of Space Sciences in Barcelona studied the X-ray emissions of 3 seemingly ordinary neutron stars. Using the Chandra and XMM Newton space telescopes, they expected to measure surface temperatures in the predictable range for their ages. Instead, they found something shocking: all 3 were between 10 and 100 times colder than their peers. This chilling result immediately challenged the assumptions encoded in most equations of state. The rate at which a neutron star cools is dictated by its interior composition. If particles within are able to shed energy efficiently, especially by emitting neutrinos, then cooling can happen far faster than standard models predict. Neutrinos, those ghost-like particles born in the sun and forged in nuclear reactions, are perfect emissaries for carrying away energy, but the degree to which they escape depends entirely on what lies at the star's core. If hyperons are present, or if matter has transformed into a superfluid or a Bose-Einstein condensate, the cooling will change drastically. In this way, each cold neutron star becomes a kind of thermometer, and what Marino's team found forced theorists to revise, eliminate, or reweight entire classes of internal models. This is the heart of the multi-messenger era of astronomy, observing the universe not just in light, but through gravitational waves, neutrinos, and other signals that cross traditional boundaries. Since GW 170817, more neutron star mergers have been anticipated and observed, though few so far have matched its clarity. Still, with each event, our models are tested anew. The hope is that one day, a merger will occur close enough, or aligned just right, to let us observe the entire process from the first ripple in space-time to the final burst of gamma rays. In such a moment, the veil may lift. Meanwhile, particle physicists continue their work underground, beneath kilometers of ice or stone, watching for signs of what lies within these cosmic anomalies. In the Antarctic, the Ice Cube Neutrino Observatory waits for a high-energy neutrino that might be born in a neutron star collision, or perhaps released in the collapse into a quark star. Other experiments attempt to simulate the pressures of neutron star cores using heavy ion collisions, briefly recreating conditions that existed moments after the Big Bang. And at the outermost limits of theory, physicists still dream of a deeper symmetry, one that combines general relativity and quantum mechanics into a single theory of everything. In this view, neutron stars are not curiosities but necessary guides. They compress mass and space into configurations that might act as test cases for string theory, loop quantum gravity, or other emerging frameworks. A neutron star may be as much a bridge to the quantum universe as the Large Hadron Collider. Their pulses, collisions, and cool silences may be data sets for the next generation of fundamental physics. There are even philosophers and cosmologists who see neutron stars as a kind of metaphor, the final act in a stellar drama, yet also a stage where the rules of the universe are rewritten. These stars are memory, fossil, and forge all at once. They remember their progenitor stars and preserve their angular momentum. They act as fossils, recording the gravitational behavior of matter under conditions unreproducible elsewhere. And they are forges, crafting the heavy elements that build planets, bones, and cities. In their silence, neutron stars speak volumes. The regular ticking of a pulsar's beam is the most precise clock in nature. Astronomers use pulsars to measure time better than atomic clocks, and to search for the slow rumble of gravitational waves from colliding galaxies. They are the metronomes of the cosmos, keeping time for an orchestra whose composition we have only just begun to decipher. And so the neutron star, once considered a dead end, becomes a new beginning. Its birth signals not just the death of a star, but the birth of insight. It connects thermodynamics to quantum mechanics, nuclear physics to cosmology, and the past of the universe to its future. In each of these collapsed stars is an unanswered question, a challenge to our hubris, a call to look deeper. One day, we may understand every layer of their interiors. One day, we may probe their cores with precision and map their magnetic fields in 3 dimensions. One day, we may even recreate neutron star conditions in the lab or discover that their matter holds the key to dark energy or quantum gravity. Until then, we look to the skies and listen to their signals, aware that the most extreme objects in the universe may also be the most illuminating. Neutron stars remind us that the universe does not just explode, it compresses. It does not just create, it remembers. And it does not just end, it transforms. They are stars that refuse to die, and in their endurance, they may reveal to us what it means to exist at all. Of all the questions we can ask about existence, perhaps the most profound is also the most unsettling. Why is there something rather than nothing? Why do you exist? Why does anyone? Why does the world, with all its beauty and brutality, its complexity and contradiction, persist at all? From the molecules in your breath to the vast galaxies spinning silently in the cosmic dark. Why are any of these things here? According to our best understanding of physics, they shouldn't be. The universe itself, its stars, its silence, its laws, and its life should never have been born. To begin unraveling this paradox, we must return to the very first instant, the birth of everything, the Big Bang. It was not merely an explosion of matter, but of space-time itself, a singular event of unimaginable energy and baffling precision. The odds that such an ordered cosmos could emerge from primordial chaos were not simply slim, they were vanishingly small. British physicist Sir Roger Penrose attempted to capture just how improbable this beginning was. His estimate, a number so staggeringly huge it defies intuition, has come to be known as the Penrose number 1 in 10 to the 10 to the 123. That is a 1 followed by more zeros than the number of atoms in the observable universe, a number so extreme that calling it impossible barely does justice to its scale. It speaks to a universe birthed not in chaos, but in breathtaking coherence, like a cosmic sculpture chiseled with infinite precision. This low entropy beginning is deeply mysterious. As time flows forward, systems tend toward disorder. It's the arrow of time. Entropy increases and order decays. We see it in the slow ruin of ancient cities and the fraying of our own bodies in the tangled knots of headphone wires left in a drawer. We expect the same of the cosmos. Black holes, as Penrose noted, are the ultimate endpoints of this decay, the graveyards of structure where complexity collapses into featureless oblivion. Yet here we are, nearly 14 billion years after the beginning, still surrounded by intricate structures, by stars, by minds, by the astonishing dance of life and matter. The universe remains astonishingly ordered. And entropy is not our only puzzle. We live in a world dominated by matter, by the particles that make up you, me, the Earth, and the stars. But every particle of matter has an opposite antimatter. And when matter meets antimatter, they annihilate each other in a flash of pure energy. So, where is all the antimatter? Why did just enough matter survive the primordial inferno to build a cosmos when our equations suggest symmetry should have ruled equal parts matter and antimatter destined to destroy each other completely? Nothing should remain. Not a single atom. And yet, improbably, something did. Then, perhaps most baffling of all, comes the issue of weight. Not of stars or galaxies, but of space itself. Quantum theory tells us that even in a perfect vacuum, energy bubbles and boils into existence. These fluctuations give empty space a weight, one that, when calculated using our best understanding of quantum fields, is staggeringly high. So high, in fact, that the moment the universe sprang into being, it should have curled back in on itself and vanished. It should have been crushed by the weight of its own emptiness. Instead, the universe expanded. Space stretched. Light emerged. Galaxies formed. The cosmos lived. This vast mismatch between theory and observation is known as the cosmological constant problem, and it haunts modern physics. It is not a subtle discrepancy. It is a chasm between the predictions of our models and the reality we observe. It tells us that something fundamental is missing in our understanding, something hidden deep in the structure of the vacuum itself. And so we are left with a troubling truth. We should not be here. Not because of a failure of imagination, but because of a failure of explanation. The universe is not just improbable, it is by all accounts impossible. And yet impossibly it is here, and so are we. What is energy? At first glance, it seems a straightforward question. Yet, beneath its surface lies one of the most profound concepts in physics, an idea that binds together the functioning of stars, the breath in our lungs, the technology we use, and even the mass of the cosmos itself. Energy is not a single entity, but a unifying thread connecting diverse processes and phenomena, from the combustion of fuel in a locomotive to the fusion of hydrogen in the heart of the sun. But understanding how we came to see it this way requires a journey not through equations, but through observation and insight, beginning with an unlikely figure aboard a 19th century sailing vessel. Julius Robert von Meyer, a ship's doctor sailing through the Dutch East Indies in the 1840s, was struck by an unusual detail. Treating sailors in the tropical heat, he noticed that the color of venous blood, the blood returning to the heart, was brighter than expected. In colder climates, such blood would appear darker, depleted of oxygen after fueling the internal combustion that keeps our bodies warm. But in the suffocating heat of the tropics, the sailors' bodies didn't need to burn as much food for warmth. Their metabolism slowed and less oxygen was consumed. The blood returning to the heart was nearly as red as when it left the lungs. This small biological observation led von Meyer to a remarkable conclusion. The energy that the body normally produces through metabolism was being supplemented by the heat of the surrounding environment. In short, heat and biological work were interchangeable. He had glimpsed a universal principle. Energy may take many forms, but it is conserved and convertible. By the mid-19th century, such ideas were beginning to coalesce into a broader framework. Scientists realized that energy could be stored, transferred and transformed, whether in the potential energy of a suspended weight, the chemical bonds of coal, or the expanding steam that powered industrial machinery. Energy, in essence, was capacity. The capacity to do work. And work in physics is the application of a force across a distance. These foundational insights prepared the stage for the 20th century, when energy would be redefined yet again, this time in the most unexpected place, in the very mass of objects. Albert Einstein's theory of special relativity, published in 1905, did more than upend our notions of space and time. It also transformed our understanding of inertia. Imagine a hypothetical scenario where an idealized human, a supercharged Usain Bolt, could be accelerated to near the speed of light. To push him faster and faster, more energy would need to be fed into the system. Yet, as his velocity approached the universal limit, his resistance to further acceleration would increase. This resistance is not arbitrary. It is inertia. And what Einstein saw was that the energy being added wasn't disappearing. It was manifesting as growing inertia. And inertia is another word for mass. In a moment of sublime clarity, Einstein saw that mass and energy are two expressions of the same fundamental thing. And this insight he captured with his most iconic formula, E equals mc2. The implications of this are profound. It tells us that even at rest, an object contains an immense amount of energy. The c in that equation, the speed of light squared, is a massive multiplier. A modest 9-kilogram object, like a small dog, contains energy equivalent to 200 megatons of TNT. This is not just theory. This mass-to-energy conversion powers nuclear weapons and fusion reactors. In both, mass is transmuted into heat, light, and kinetic energy. And in the cores of stars, including our Sun, this process sustains the very existence of life on Earth. Hydrogen nuclei fuse into helium, releasing energy as they lose tiny amounts of mass. The difference is minute but multiplied across a star's lifetime. It becomes monumental. Einstein's revelation also changed the way we think about gravity. In Newton's formulation, gravity pulled on mass. But Einstein, having unified mass and energy, realized that gravity must pull on energy as well. Light, though massless, is bent by gravity because it carries energy. This is not a metaphor. It is a measurable, observable phenomenon. Light from distant stars is deflected as it passes near massive bodies, an effect confirmed during the solar eclipse of 1919 and now seen routinely in the lensing of galaxies. So when physicists ask how much something weighs, they are not concerned solely with its mass. They are asking about its total energy content. This includes not just the rest mass of the object, but also its kinetic energy, its internal energy, and even the energy contained in the space around it. The universe therefore has a weight, and that weight is determined not only by the visible matter star's gas dust, but also by radiation kinetic motion, and most mysteriously the vacuum itself. This brings us to the heart of modern cosmology. The mass-energy content of the universe is the source of its gravitational behavior, and when we survey the cosmos we see a surprising pattern. The visible matter accounts for a mere fraction of the total energy budget, roughly 5%. Dark matter, an unseen but gravitationally active substance, accounts for another 25%. The remaining 70% is something stranger still: dark energy, an invisible component permeating empty space and driving the accelerated expansion of the universe. This is where the concept of energy becomes most enigmatic. The vacuum, seemingly empty, is not truly void. Quantum field theory tells us that even in the absence of particles, energy remains. Virtual particles pop in and out of existence, borrowing energy on short timescales in accordance with the uncertainty principle. But this vacuum energy carries weight and gravity responds to it. The cosmological constant, Einstein's term for the energy density of the vacuum, exerts a repulsive force causing space itself to expand. When physicists attempt to calculate this vacuum energy using quantum theory, they arrive at a catastrophic number, many orders of magnitude higher than what is observed. The difference between theory and reality is one of the greatest in all of science. This is the cosmological constant problem. The energy of the vacuum should be so immense that the universe would have torn itself apart at birth, and yet it did not. Something is missing in our understanding, some piece of the puzzle not yet found. So, what is energy? It is heat and light motion and mass radiation and gravity. It powers stars and sustains life, and it defines the weight of the universe itself. From the biological insight of a 19th century physician to the relativistic revolutions of the 20th century, our conception of energy has evolved into something profound and mysterious. As we turn our instruments to the skies and attempt to weigh the cosmos, we are not just measuring mass. We are measuring the energy of everything, the visible, the invisible, and perhaps the unknowable. How much does the universe weigh? In the 3rd century BCE, in the city of Syracuse, the great mathematician Archimedes turned his mind toward a question that, though deceptively simple in phrasing, demands the loftiest intellectual tools to address how many grains of sand could fit inside the cosmos. In his treatise, known as the Sand Reckoner, Archimedes dismissed the notion that the quantity of sand in the universe was infinite, and instead set out to calculate a number one anchored in tangible, measurable quantities, beginning with the width of a poppy seed and extrapolating to the entire celestial sphere. This endeavor led him to construct an entirely new numerical system, and by estimating the universe to be a sphere centered on the sun and bounded by the fixed stars, he concluded that it would contain no more than 163 grains of sand. The estimate, astonishingly close to modern conceptions of the universe's mass-energy content, was of course a numerical coincidence, since Archimedes was constrained by the astronomical knowledge of his day. Nonetheless, his desire to quantify the cosmos laid conceptual groundwork that resonates even now. Today, we no longer speak in terms of poppy seeds and grains of sand, but in terms of energy mass, space-time curvature, and quantum fields. When cosmologists ask how much the universe weighs, they are not weighing celestial bodies with scales, nor are they tallying particles one by one. Instead, they are evaluating how much total energy exists within the observable universe, and how that energy in all its various forms distorts the fabric of space-time. This, in essence, is the weight of the universe, not a weight in the Newtonian sense, but a measure of the energy content that governs the gravitational dynamics of the cosmos. To estimate such a quantity, one must first delineate what is meant by the universe. More precisely, scientists focus on the observable universe, that portion of the cosmos from which light has had time to reach us since the Big Bang, roughly 138 billion years ago. One might initially suppose that this corresponds to a sphere 138 billion light-years in radius, but that would be an oversimplification. Due to the expansion of space over cosmic time, the most distant galaxies we can observe today are actually around 465 billion light-years away. This defines the radius of our observable universe, making its diameter nearly 93 billion light-years. This sphere encompasses all that we can potentially observe, but not necessarily all that exists. Beyond its horizon may lie further galaxies, further structures, perhaps even regions governed by different laws of physics. We simply do not and cannot know. For our purposes, however, we restrict ourselves to the observable universe, and within that finite yet vast domain, we attempt to sum up the total energy content. We begin with stars. The Sun. An average-sized star has a mass of approximately 2 × 1030 kilograms. The Milky Way galaxy contains an estimated 100 to 400 billion stars, amounting to a stellar mass of about 1042 kilograms. There are at least 200 billion galaxies in the observable universe, each containing roughly 100 billion stars, suggesting the total stellar mass is approximately 2 × 1052 kilograms. This is already an enormous figure, but it accounts only for the luminous material stars and perhaps planets and visible interstellar gas. However, much of the universe's matter is not luminous. A more precise measurement comes from analyzing the effects of matter and energy on the geometry of the universe itself. One of the most powerful tools for doing so is the study of the cosmic microwave background radiation, or CMB, the afterglow of the Big Bang, now cooled to just 27 Kelvin. This ancient radiation carries with it the imprints of the universe's earliest fluctuations in temperature and density fluctuations that seeded the formation of galaxies and large-scale structure. Using data from satellites such as COBE, WMAP, and Planck, cosmologists have measured minute temperature variations in the CMB across the sky, and from the statistical properties of these variations inferred the density and composition of the universe with remarkable precision. From these measurements, we now estimate the total mass energy content of the observable universe to be approximately 15 × 1053 kilograms. This includes not only the visible stars and gas, but also all matter, baryonic and non-baryonic, and radiation. And when we convert this mass into energy using Einstein's famous relation E equals mc2, we find the equivalent of about 135 × 10⁻⁷ joules of energy. It is an incomprehensibly vast reservoir, yet it represents only a small fraction of what the universe actually contains. That is because the visible matter, the atoms that compose stars, planets, and people, accounts for only about 5% of the universe's total energy content. The rest is composed of two enigmatic components: dark matter and dark energy. Dark matter is a form of matter that does not emit, absorb, or reflect light. It interacts gravitationally but not electromagnetically, making it invisible to our instruments. Its existence is inferred from its gravitational effects on the rotation of galaxies, the dynamics of galaxy clusters, and the bending of light from distant sources via gravitational lensing. Dark matter comprises about 27% of the universe's energy budget. Yet, even dark matter is not the dominant component. That distinction belongs to dark energy, an even more mysterious substance that constitutes roughly 68% of the total. Unlike dark matter, which pulls structures together through gravity, dark energy is responsible for the accelerated expansion of the universe. Its effects were first observed in the 1990s through studies of distant Type Ia supernovae, which appeared dimmer than expected, suggesting that the rate of cosmic expansion had increased rather than slowed over time. Dark energy behaves differently from all other forms of matter and radiation. It has an energy density that remains constant as the universe expands. This is deeply counterintuitive. Ordinary matter becomes more dilute as the universe stretches. So does radiation, whose energy per photon also diminishes. But dark energy remains the same per unit volume. This implies that as space expands, new dark energy is created, a bizarre but consistent consequence of general relativity when applied to a vacuum with energy. This vacuum energy, referred to variously as the cosmological constant, the zero-point energy, or the vacuum expectation value, permeates all of space. Quantum field theory tells us that even in a perfect vacuum where no particles exist, quantum fields are never truly at rest. They fluctuate constantly, creating short-lived virtual particles that emerge and vanish in a seething quantum froth. These fluctuations contribute energy to empty space, and that energy gravitates. It bends space-time just like mass does. This vacuum energy, according to quantum theory, should be enormous. So enormous, in fact, that it would have curved the universe into oblivion in a fraction of a second after the Big Bang. This brings us to one of the most profound problems in modern theoretical physics, the cosmological constant problem. The discrepancy between the predicted and observed values of the vacuum energy is not merely large. It is the largest known disagreement between theory and observation in all of science. Quantum field theory predicts a vacuum energy density that is 120 times greater than the observed value. This is a number so large that it defies imagination. It suggests that if the vacuum energy were truly as predicted, the universe would have imploded almost immediately after its creation. No stars, no galaxies, no structure, certainly no life would ever have formed. And yet, here we are. The vacuum. Energy, for reasons no theory currently explains, is small. Astonishingly small, yet non-zero. It is precisely the right magnitude to allow for a universe that grows slowly over billions of years. A universe that permits the emergence of complexity biology and consciousness. This apparent fine-tuning of the cosmological constant remains one of the greatest mysteries in cosmology. It suggests either an underlying principle yet to be discovered, or perhaps a selection effect in a multiverse scenario where many universes exist, each with different vacuum energies, and we find ourselves in one of the rare few where conditions are right for life to emerge. In total, when dark energy is included, the full energy of the observable universe converted into the TNT equivalent to illustrate its staggering scale amounts to approximately 67 × 10^54 kilograms of mass energy, or roughly 60 × 10^71 joules. But this energy, vast as it is spread thinly across the immense volume of space. The average energy density of the universe is incredibly low, less than a few hydrogen atoms per cubic meter, and dark energy even more diffuse. A coffee cup filled with vacuum energy contains less energy than the kinetic energy of a falling mosquito. It is only because space is so vast that these small quantities add up to such a significant gravitational influence. And so, in the final reckoning, our universe is not massive because it is densely packed with material, but because it is so vast. Its weight in the sense of total energy emerges from the product of low density and enormous volume. And within that volume lies not only all the matter and energy we can see, but all the structure that makes up the cosmos, from stars and galaxies to clusters and filaments, emerging and evolving under the inexorable influence of gravity. To weigh the universe, then, is not merely to count stars or some particles. It is to measure the full story of cosmic energy in all its forms, to understand how the vacuum itself contributes to the architecture of the cosmos, and to confront the greatest mysteries that theoretical physics has yet to solve. Why does the vacuum weigh so little? Why is the cosmological constant not immense? And what principle of nature carved such an exquisitely balanced universe, one vast enough to grow old, stable enough to form galaxies, and gentle enough to allow us to ask at last just how much it weighs? The nullpunct's energy. What is the true nature of empty space? Could the vacuum itself, seemingly so inert, so devoid of structure, conceal an energy so immense it challenges the very survival of the universe? To begin unraveling this mystery, we must return to a moment nearly a century ago, to the vibrant city of Hamburg, a beacon of intellect and science in post-war Germany. There, in a modest cafe overlooking the tranquil waters of the inner Ulster, two physicists, friends, and colleagues shared a conversation that in hindsight stood at the precipice of one of the greatest cosmological enigmas of our age. Otto Stern, a cultured man with a passion for good wine and better company, leaned in to make his case. He was animated, brandy in hand, eyes bright with conviction. His friend across the table, Wolfgang Pauli, bore a fading black eye, the remnants of a barroom scuffle in Hamburg's raucous St. Pauli district. Though their temperaments diverged, Stern, the affable bon vivant Pauli, the volatile iconoclast, they were united in their pursuit of physics at its most fundamental. That day, they debated a concept now known to us as the vacuum energy, or, in German, the Nullpunktsenergie, the zero-point energy. Stern argued from observation, invoking data from the vapor pressures of neon isotopes. The discrepancy, he calculated, could not be reconciled without invoking the subtle presence of this ever-present energy, lurking even in the absence of matter. Pauli, characteristically skeptical, countered with a stark warning. If the Nullpunktsenergie truly existed in the quantity that quantum theory implied, it would have profound gravitational consequences. The universe, he claimed, wouldn't extend beyond the distance from Earth to the Moon. It would collapse upon itself under the weight of its own vacuum. This disagreement, passionate, personal, and profound, marked one of the earliest acknowledgments of a paradox that continues to confound physicists to this day. The idea that empty space might contain energy wasn't new. As early as 1911, Max Planck had speculated about zero-point fluctuations, suggesting that even in the absence of all matter and heat, a residual energy might remain. A few years later, Walter Nernst took the bold step of proposing that this energy might pervade all of space, an all-pervasive invisible sea of latent potential. Yet it was Albert Einstein who introduced a separate but ultimately related concept, the cosmological constant, a term added to his general theory of relativity in 1917 to balance the gravitational pull of matter and achieve a static universe. Einstein's relationship with these ideas was complicated. Initially, he supported the cosmological constant as a mathematical necessity. He even collaborated with Stern to estimate the impact of zero-point energy on hydrogen molecules, but he failed to connect the two concepts, as observations revealed that the universe was not static but expanding. Einstein famously recanted his cosmological constant, referring to it allegedly as his biggest blunder. Likewise, he distanced himself from zero-point energy, deriding its mention with a self-deprecating smirk. But time would show that both the constant and the vacuum energy were far more than mathematical curiosities. They were central to the workings of our universe. The turning point came in the 1920s. as quantum mechanics rose from the mathematical mist. On the island of Helgoland, beset by allergies and insomnia, Werner Heisenberg wrestled with the spectral lines of hydrogen atoms. There, amidst the dunes and salty air, he formulated what would become the uncertainty principle, an insight into the intrinsic unpredictability of nature at the smallest scales. Heisenberg's principle asserted that certain pairs of physical properties like position and momentum could not be simultaneously known with arbitrary precision, and from this the idea of zero-point energy naturally followed. If a particle could never be precisely at rest, then even in its lowest energy state it must possess some residual motion, some irreducible energy. To visualize this, imagine placing a marble in the bottom of a smooth bowl. In the classical view, it settles motionless at the lowest point, its energy fully expended, but in the quantum world such rest is forbidden. To know its position exactly would require complete ignorance of its momentum. Therefore, even at absolute zero, the marble must jiggle, however faintly. That jitter, imperceptible though it may be, corresponds to a real energy. Now, replace the marble with a subatomic particle, and the bowl with a quantum field. What you discover is that the vacuum itself can never be truly still. It writhes with fluctuations, virtual particles forever appearing and vanishing in a foam of probabilistic activity. These aren't particles in the traditional sense. They cannot be touched, weighed, or isolated. They don't leave direct tracks in detectors, but their effects are real. These vacuum fluctuations give rise to measurable forces. The Casimir effect, discovered by Dutch physicist Hendrik Casimir, is a striking example. When two uncharged metal plates are brought close together in a vacuum, they experience an attractive force not from electromagnetic interactions, but from the change in vacuum energy between them. This force is real enough to be measured. It even plays a role in the ability of geckos to cling to walls through the subtle van der Waals forces that arise from quantum vacuum effects between molecules. So, if vacuum energy is real, and if it can produce measurable forces, how much of it is there? This is where the problem begins. Physicists like Pauli attempted early estimates by partitioning space into tiny boxes. Imagine dividing a coffee cup of vacuum into infinitesimal regions, each allowed to contain virtual particles with energy limited by the uncertainty principle. Using the best resolution of their time, Pauli and his contemporaries imagined a cutoff scale around a femtometer, the approximate size of a proton. Even at this conservative scale, they found a staggering amount of energy in empty space, enough in a single coffee cup to boil away all the oceans of Earth. Fast forward a century, and we have probed much deeper into the quantum realm. With the Large Hadron Collider smashing particles together at near light speed, we can now resolve distances 100,000 times smaller than a proton. If we use these more refined scales in our vacuum energy calculations, the numbers spiral out of control. The energy density becomes so immense that a coffee cup of empty space could vaporize entire planets, indeed, entire galaxies, again and again. Go further still down to the Planck scale, the smallest scale at which space and time still retain meaning, and the energy becomes truly catastrophic. At this scale, a single coffee cup of vacuum could contain enough energy to obliterate all matter in the observable universe a trillion times over. And yet, paradoxically, we see none of this space, for all its emptiness behaves gently. The expansion of the universe is slow. Measured, delicate galaxies drift apart. Yes, but the very fabric of space is not heaving under the unimaginable weight of vacuum energy. The catastrophic predictions of theory are not reflected in reality. This is the essence of the cosmological constant problem. You see, in general, relativity, gravity, is not a force in the traditional sense. It is geometry. Energy and mass tell space. How to curve in curved space tells matter how to move. All forms of energy contribute to this curvature, not just matter but also light radiation and crucially vacuum energy. If vacuum energy is indeed as large as quantum field theory predicts, then its gravitational influence should be overwhelming. The curvature it imposes on space-time should be so extreme that the universe would not just collapse, it would never have emerged in the first place. There would have been no stars, no galaxies, no time for atoms to form or life to arise. The cosmos born a super heavyweight would have folded in on itself in an instant. But we are here. The universe exists. The observable cosmos stretches 47 billion light-years in every direction. It is filled with stars, planets, life, and the slow unfolding of time. Somehow, the vacuum energy we measure through observations such as the acceleration of cosmic expansion is not large. It is minuscule. It is 120 orders of magnitude smaller than what theory predicts. That discrepancy, a factor of 10^120, is the largest known between theory and observation in all of physics. It is not a minor oversight. It is a yawning chasm, a crisis. So what might resolve this paradox? Some have speculated that there is a mechanism currently unknown that cancels the vacuum energy almost perfectly, leaving just a tiny residual effect. Others have turned to the anthropic principle, arguing that we observe a small cosmological constant because universes with larger values would collapse too quickly for observers like us to evolve. In this view, the multiverse, a landscape of infinite universes, each with its own physical constants, might explain why we find ourselves in a universe so finely tuned for life. And there are those who suggest that we have misunderstood gravity itself. Perhaps general relativity, elegant though it is, fails to account for the true interaction between quantum energy and space-time curvature. Maybe a new theory, a quantum theory of gravity, will one day reveal a hidden structure that tames the vacuum and explains why its energy doesn't wreak havoc on the cosmos. Until then, the nullpunkt's energy remains a mystery, both tantalizing and terrifying. It whispers to us from the vacuum, hinting at hidden depths, inviting us to reconcile the elegance of quantum mechanics with the curvature of the cosmos. It is the silent architect of the cosmological constant problem, and it is a problem that demands our attention, not merely as a matter of scientific curiosity, but as a profound clue to the architecture of reality itself. In the end, what Polly and Stern debated over their coffee in Hamburg was more than academic. It was a glimpse into the abyss, the recognition that beneath the surface of what we call empty space lies a storm of quantum unrest, a surging sea of possibility whose true weight we still struggle to comprehend. The universe, it seems, is far more fragile and far more finely tuned than we ever dared to imagine. The cosmological constant problem. In the early autumn of 1949, a seemingly innocuous observation from a weather reconnaissance flight would mark a turning point in global history. A filter paper aboard a U.S. weather plane flying its usual route from Japan to Alaska registered an anomalous spike in atmospheric radioactivity. The filter was dispatched to Los Alamos for further analysis. There, the results were decisive. On September 23rd, President Harry Truman publicly confirmed that the Soviet Union had detonated its first atomic bomb. The nuclear arms race had begun. Beneath the shock waves of this geopolitical shift lay another moment of historical significance, perhaps less immediate in its consequence, but far more enduring in its reach. Just south of the explosion site at Semipalatinsk, Kazakhstan, 8 men sheltered in a trench observing the dawn of the Soviet nuclear era. Among them was Yakov Zeldovich, a towering figure in theoretical physics and head of the Soviet Union's nuclear theory division at Arzamas 16. Zeldovich's contributions to his nation's atomic program were immense, and within Soviet scientific circles he was revered. Yet his intellect extended far beyond the confines of weapons development. He was one of the rare physicists who could effortlessly traverse the frontiers of particle physics, general relativity, astrophysics, and cosmology. 2 decades after witnessing that terrifying mushroom cloud, Zeldovich would play a pivotal role in illuminating one of the most profound and unresolved enigmas in modern theoretical physics: the cosmological constant problem. By the late 1960s, the theoretical frameworks of the 20th century had achieved a remarkable level of maturity. Einstein's general theory of relativity had been tested against the precision of astronomical data and emerged victorious. It redefined gravity not as a force, but as the curvature of space-time caused by the presence of energy and momentum. Meanwhile, quantum field theory had become the dominant lens through which physicists viewed the subatomic world, a powerful amalgam of quantum mechanics and special relativity that described particles as excitations of underlying quantum fields. And yet, when Zeldovich brought these two towering pillars together, he encountered a contradiction so severe that it threatened the internal consistency of the entire edifice of theoretical physics. Zeldovich recognized that the vacuum of space, far from being a passive void, should be a dynamic and turbulent arena, one populated by incessant fluctuations of quantum fields, spawning virtual particles that blinked into and out of existence at unimaginable frequencies. According to quantum field theory, these ephemeral ripples carry energy. But in Einstein's theory, energy in all its forms curves space-time. Therefore, the vacuum itself should act as a gravitational source. It should bend the very shape of the universe. But if this vacuum energy, the so-called nullpunkts energy or zero-point energy, really existed in the amounts predicted by quantum theory, its gravitational impact would be catastrophic. Zeldovich calculated that the vacuum energy predicted by quantum field theory should curve space-time so violently that the universe would collapse into a singularity before atoms, stars, or galaxies had a chance to form. In his own words, clarifying the magnitude of the problem would carry tremendous fundamental significance for our understanding of nature. Here was a paradox that placed two of physics' most successful theories in direct conflict. Of course, this tension was not entirely new. Wolfgang Pauli, decades earlier in the 1920s, had pondered the gravitational consequences of vacuum energy. In a famous anecdote from a cafe in Hamburg, Pauli purportedly estimated the gravitational influence of the nullpunkts energy, and concluded that a universe endowed with such energy could not even extend as far as the moon. His calculation, more intuitive than precise, was dismissed by some as fanciful. Yet Zeldovich, working with the more refined tools of post-war theoretical physics, reached a similar but far more rigorous conclusion, and he made the scientific community take notice. So, how do we reconcile this prediction with the universe we observe? After all, our universe is vast and ancient. It stretches 93 billion light-years across in every direction. And it has hosted galaxies, stars, planets, and life for over 13 billion years. If quantum field theory insists that empty space contains an immense, even infinite energy density, why hasn't this energy obliterated the cosmos? This is the cosmological constant problem, and it remains one of the most significant open questions in theoretical physics. On one hand, quantum field theory predicts a staggeringly large vacuum energy. On the other hand, observational cosmology, particularly measurements of the accelerating expansion of the universe, tells us that the actual energy density of the vacuum is small, very small. About 120 orders of magnitude smaller than the value predicted by naive calculations from quantum field theory. It is this discrepancy, sometimes described as the worst theoretical prediction in the history of physics, that demands an explanation, and the stakes are enormous. Resolving this conflict would likely require a radical reimagining of the fundamental principles that govern the universe. One school of thought advocates for a purely empirical approach. Ignore the theory, trust the data. If observations tell us that the vacuum energy is small, then so be it. Perhaps quantum field theory, despite its extraordinary success in describing particle physics, is simply inadequate at describing the vacuum structure of the universe. Yet, this route offers little comfort to those searching for a unified theory of nature. It amounts to giving up on our best theoretical tools, just because they yield the wrong answer. Scientists, by their nature, are not content with that. And so the search continues. Theoretical physicists have proposed a wide range of ideas over the past half-century. Some argue that vacuum energy from quantum fields must be counterbalanced by contributions from other, as yet undiscovered sectors of the universe. Perhaps there exists a new field or mechanism that cancels out the enormous contributions predicted by known particles. But for such a cancellation to yield a net energy density as small as what we observe would require a precision of 1 part in 120, a level of fine-tuning that borders on the absurd. It is like balancing the mass of a trillion suns against an equal weight accurate to the mass of a single electron. Others have taken a more radical path. One of the most controversial yet tantalizing ideas involves the multiverse. According to this view, our universe is just one of many, perhaps an infinite number, each with its own physical laws, constants, and vacuum energies. In most of these universes, the vacuum energy is either too large and positive, blowing the cosmos apart before galaxies can form, or too large and negative, collapsing it in a catastrophic big crunch shortly after birth. But in a tiny subset of these universes, the vacuum energy happens to fall within a narrow range compatible with structure formation and eventually life. This is the anthropic argument. We find ourselves in a universe with a small cosmological constant, not because it had to be that way, but because we couldn't exist in a universe where it wasn't. The vacuum. Energy may well be a random parameter drawn from a vast ensemble of possibilities. The string theory landscape, as it is known. Depending on how one counts, this landscape might contain as many as 2,500 or even 10 to 7,000 possible vacuum states, each with a different value for the cosmological constant. In this picture, the problem is not why the vacuum energy is so small, but rather why it is small enough for us to be here asking the question. This line of reasoning has both defenders and critics. Some physicists, like Nobel laureate Steven Weinberg, have shown that the anthropic approach can make testable predictions. In the late 1990s, Weinberg and his collaborators argued that if dark energy, the observational manifestation of the cosmological constant, constituted less than 60% of the total energy density of the universe, the anthropic explanation would be invalid. But observational data from distant supernovae soon confirmed that dark energy accounts for about 70% of the universe's energy budget, thus passing this predictive hurdle. Still, many theorists are uneasy with anthropic reasoning. They argue that it undermines the predictive power of science. If any observed value can be explained post hoc by appealing to selection effects in an unobservable multiverse, then what becomes of falsifiability, the bedrock of the scientific method? In the meantime, other speculative ideas continue to surface. Concepts such as vacuum energy, sequestering supersymmetric large extra dimensions, or modified theories of gravity offer alternate routes to solving the cosmological constant problem, yet none has emerged as a definitive solution. The problem remains stubbornly unsolved. What is clear is that this mystery lies at the heart of our quest to understand the universe. It is a deep wound in the otherwise elegant framework of modern physics. The cosmological constant problem is not merely an error to be corrected. It is a signpost pointing toward a more profound theory, a missing piece of the cosmic puzzle. It is deeply ironic that the substance causing us so much confusion is nothing at all empty space, or rather what we once thought was empty. We now know the vacuum is anything but empty. It is a seething, energetic ocean, bubbling with virtual particles and quantum fluctuations, and yet its energy density is almost imperceptible, so small that a coffee cup of vacuum holds less energy than it takes to swat a fly. So small that it has allowed the universe to expand slowly to grow old, to form galaxies, stars, planets, and ultimately life. And so, we return to where we began. We set out to weigh the universe. We measured the masses of stars and galaxies, the halos of invisible dark matter, and the faint glow of the cosmic microwave background. We measured the vacuum itself. And what we found was not a crushing burden, but a delicate balance, a cosmos surprisingly light, improbably gentle, a universe that should not have existed and yet does. And so, the question remains, why is the vacuum energy so small? Why hasn't the universe been destroyed by the weight of its own empty space? What is the true nature of the nullpunk's energy? These are not just questions for physicists. They are questions about existence itself, about why the universe looks the way it does, about why we are here at all.
What would you see if the universe forgot to build stars around you? What would it feel like to drift in a place so vast and hollow that light itself seems to have given up? Can you imagine a void so immense, so unfathomably empty, that the very notion of existence feels like a myth? Close your eyes, picture yourself floating alone in a super void, an immense sphere of darkness where the very fabric of the cosmos feels unfinished. There are no stars, no galaxies, no soft glow of clustered starlight to anchor your place in the universe. With the naked eye, or even the power of an amateur telescope, you see nothing. No Orion, no Andromeda, no comforting map of constellations we once used to navigate both oceans and imagination. To you, the universe would feel truly empty. And yet, this place exists. It is not fiction, but fact, known as the Boötes Void. This cosmic cavern spans 330 million light-years across a chasm so large, the Milky Way could vanish into it millions of times over. Despite its gargantuan volume, roughly 1 million cubic megaparsecs, where we would expect thousands of galaxies to cluster and dance in gravitational spirals, astronomers have observed a mere 60 galaxies scattered like whispers in the dark, faint spiral, and blue echoing the birth cries of young stars forming in isolation. Astronomer Greg Aldering once remarked that had the Milky Way formed within the center of this void, we would not have discovered the existence of other galaxies until the 1960s. That's how barren, how deceptively silent this region of the cosmos is. Imagine if Earth lay on one edge of this void. The light from the opposite side would only just now be arriving, carrying stories from a time when amphibians still crawled through primordial swamps millions of years before even the first dinosaur opened its eyes to the sun. The Boötes Void, often called the Great Nothing, defies our expectations of cosmic structure. According to our understanding, the age of the universe places a strict limit on how large any coherent structure can be. No galaxy cluster, no cosmic filament, no void should exceed several tens of millions of light years in diameter. And yet here we are, confronted by a structure that shatters that threshold, a supervoid that challenges the very rules we thought governed the universe. Its presence tells us something, though. The few galaxies that do reside within it are not randomly strewn, but instead follow a linear, almost tubular pattern. It is as if we are seeing the fragmented ruins of a wall, a cosmic boundary crumbled between two adjacent voids. Individually, these voids make sense, but collectively, they form a structure beyond what cosmic evolution alone should allow. Even in this cosmic abyss, this supposed great nothing matter still finds a way to cling to structure, light still finds a way to be born. Yet to glimpse true darkness, to peer into the deepest recesses of time and space, we must look beyond even the Boota's void. We must travel not just across distance, but backward through time, to an epoch before stars, before galaxies, before light itself. This is the era cosmologists call the Cosmic Dark Ages. For nearly 200 million years after the Big Bang, though the universe possessed all the raw ingredients needed to forge stars, no star had yet ignited. There was no light, only cooling hydrogen-helium and the silent seeds of future galaxies. The darkness was not metaphorical, it was literal, total, and enduring. A silence so absolute that the cosmos itself seemed to be holding its breath. And so we must ask, why did the universe wait so long to turn on the lights? What does this long, unilluminated pause reveal about the galaxies we see today? How can we possibly understand an era where there was no light to guide us? From Copernicus, who displaced the Earth from the center of the solar system, to Hubble, who revealed our galaxy to be one among billions, the history of cosmology has been a series of humbling revelations. We are not the center of anything, not the solar system, not the galaxy, not even the universe. The deeper we look, the more we realize how small our place is and how vast the mystery still remains. The edge of darkness, observing the threshold between light and night. In the annals of observational cosmology, few moments have marked a turning point as sharply as the Hubble Deep Field exposure of 1995. This historic event did not begin with grand discoveries or triumphs, but rather from skepticism, pressure, and a bold scientific intuition. The Hubble Space Telescope, the crown jewel of astronomical instrumentation, had endured a tumultuous debut. Its launch into low Earth orbit had been met with both optimism and public scrutiny, amplified when the first images returned from space were far from the clarity scientists had anticipated. Despite Hubble's mirror being one of the smoothest and most precisely ground optical surfaces ever created, a minuscule aberration less than 1/50th the width of a human hair resulted in devastating image blur. The collected photons failed to converge accurately, and the telescope's great promise seemed to unravel into failure. However, Hubble's low Earth orbit, which could have been a logistical limitation, became a saving grace. A crude servicing mission by NASA astronauts was able to correct the flaw through an ingenious optical fix, a series of small corrective lenses, not unlike those in a pair of glasses. With its vision restored to sharpness, Hubble was back in the game, but its credibility still needed defending. Under political pressure and scientific expectation, Robert Williams, the then director of the Space Telescope Science Institute, was allotted discretionary observing time hours. He could spend observing anything in the cosmos. What he chose shocked his peers. Rather than direct Hubble's unprecedented sensitivity toward a known target, a star-forming region, a prominent nebula, or a supernova remnant, Williams decided to point the telescope at what was effectively nothing. A tiny, seemingly empty patch of sky in the northern hemisphere covering an area no larger than 1/30th. The diameter of the full moon was selected. To the human eye and to all previous telescopes, it was devoid of structure or light. There were no visible stars or galaxies. It was a celestial void. For 10 continuous days, Hubble gazed at this darkness. With each passing hour, its deep field camera gathered the feeble, ancient photons arriving from the farthest recesses of the universe. This act of patience and vision culminated in the Hubble Deep Field, a single image that contained thousands of galaxies, each a sprawling collection of billions of stars suspended in space and scattered across time. It was an astronomical revelation. What had once seemed like emptiness was in fact a dense thicket of galactic forms, spirals, ellipticals, irregulars, red, blue, and everything in between. But this image was more than just a cosmic census. It was a temporal map. Every point of light captured was not only distant in space, but also in time, due to the finite speed of light. Observing faraway galaxies is equivalent to looking into the deep past. The farther away the galaxy, the longer its light has traveled, and the further back in time we are observing. Some of the galaxies in the Hubble Deep Field appeared as they were billions of years ago, close to the time when galaxies first began to form. To interpret this phenomenon with rigor, cosmologists conceptualize the observable universe as a set of concentric spherical shells centered on the observer. Each shell represents a greater light travel distance and therefore an earlier epoch. The light from our sun takes approximately 8 minutes to reach us, placing it in our innermost shell. The light from the Andromeda Galaxy, our nearest galactic neighbor, takes about 5 million years, carrying with it the image of that galaxy as it existed when early hominids like Homo habilis roamed the Earth. This ladder of light time continues outward. With advanced telescopes like Hubble and now James Webb, we can peer out to shells whose light began its journey just a few hundred million years after the Big Bang. These earliest visible galaxies, little more than red smudges, are some of the universe's primordial stellar systems. As feeble as these signals are, modern instruments allow us to dissect their light using spectroscopy. The same principles that govern the Doppler shift of a passing ambulance's siren apply to light. When a galaxy recedes from us, its emitted light stretches into longer wavelengths, a phenomenon known as redshift. Chemical elements emit light at known frequencies. When we observe their spectral lines shifted into the red end of the spectrum, we can quantify how fast the galaxy is moving away. Edwin Hubble, whose work underpins modern cosmology, famously discovered that the farther a galaxy is, the faster it is receding. This empirical relationship became foundational to the Big Bang model. In this way, redshift becomes a tool not only for measuring distance, but also for ordering galaxies chronologically. As we analyze deep field images, we are peeling away the layers of cosmic history, eventually arriving at the first luminous structures to emerge after the dark birth of the universe. The most recent deep field images from the James Webb Space Telescope offer an even sharper look into this past. A single frame, covering a region of sky the size of a grain of sand, reveals thousands of galaxies, many dating back to a few hundred million years after the cosmic beginning. Yet there is a limit, a frontier beyond which even our most sophisticated instruments cannot penetrate. This is not merely a technological boundary, it is a fundamental limit of physics. Beyond a certain point, we arrive at a time before stars had ignited, before galaxies had formed, before there was any visible light at all. We call this epoch the Cosmic Dark Ages. To understand this profound darkness, one must return to the early radiation-dominated universe. Immediately following the Big Bang, the cosmos was a seething plasma of photons, electrons, and baryons. Light could not travel freely as it constantly scattered off free electrons, keeping the universe opaque. This state persisted until about 380,000 years after the Big Bang, when the universe cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms, a period known as recombination. With fewer free electrons to scatter photons, the universe became transparent for the first time. The radiation released at this moment, the cosmic microwave background, still bathes the universe today. However, although photons were now free to travel, the light emitted during recombination has been redshifted by the expansion of the universe. Originally a warm orange glow, it gradually stretched into the infrared and now into the microwave range. The universe cooled and visible light disappeared. The cosmic embers of creation dimmed into darkness. For nearly 200 million years, the universe entered a period devoid of any sources of visible light. The matter was too diffuse and too cool for nuclear fusion. There were no stars, no galaxies, and thus no new light. During this long night, another invisible actor played a critical role. Dark matter, first identified indirectly by Vera Rubin and Kent Ford in the 1960s, dark matter's gravitational influence was needed to explain the unexpectedly high orbital velocities of stars within galaxies. According to Newtonian physics, stars orbiting at great distances from the galactic center should move more slowly. Instead, observations revealed that they maintained high speeds, implying the existence of unseen mass exerting additional gravitational pull. This mass, which does not emit, absorb, or reflect light, was termed dark matter. It is now estimated to comprise about 80% of the universe's total matter content. The behavior of dark matter is profoundly different from that of ordinary baryonic matter. While normal matter interacts through both gravity and electromagnetism, allowing it to cool by emitting radiation, dark matter interacts only via gravity. This means that as dark matter collapses under its own gravity, it cannot radiate away thermal energy. Without this cooling mechanism, gravitational contraction is arrested when the pressure from random thermal motion balances the inward pull of gravity. Consequently, dark matter structures form vast diffuse filaments and halos but never condense into stars or planets. During the cosmic dark ages, dark matter formed a hidden skeleton upon which the future large-scale structure of the universe would be built. The absence of visible light does not imply the absence of structure. The dark matter filaments formed a complex cosmic web with nodes of high density, forming halos into which baryonic gas would later fall. These halos provided the gravitational wells necessary to accumulate and compress gas, setting the stage for the first stars. But for this to happen, the gas itself had to cool, condense, and eventually trigger fusion. Unlike dark matter, normal gas clouds can cool through atomic interactions. As atoms collide, electrons become excited to higher energy levels. When they relax back to their ground states, they emit photons, carrying away energy and reducing the internal pressure. Over time, this radiative cooling allows the cloud to collapse further, increasing in density until the conditions for nuclear fusion are achieved. In this way, the first stars, known as population 3 stars, were born. These stars were likely massive, short-lived, and composed almost entirely of hydrogen and helium, lacking the heavier elements synthesized by later generations of stars. Detecting these primordial stars directly remains one of the most elusive goals in astrophysics. Their faintness, great distance, and short lifespans conspire to hide them from even our most sensitive telescopes. Nevertheless, their indirect fingerprints may yet be found in the chemical composition of later stars, in the rayonization history of the intergalactic medium, and in the subtle distortions they imprint upon the cosmic background light. And so we return to the present. Our telescopes stationed above the Earth's atmosphere, armed with mirrors and spectrographs, continue to gaze into the void, not out of despair, but out of curiosity. The darkness is not empty, it is filled with structure, with memory, with signals stretched thin by time and space. From the glowing fog of recombination to the cool embers of the cosmic microwave background, from the hidden scaffolding of dark matter to the first glimmers of starlight, the universe reveals itself not in brightness but in persistence. As we trace the universe backward, peeling away the layers of time, we approach a limit beyond which no light was ever cast. And yet the questions persist. How did the universe first ignite? What mechanisms seeded the galaxies and clusters? We now see what lies beyond the observable horizon. These questions remain unanswered but not unreachable. The edge of darkness is not the end of knowledge, it is the beginning of insight. It is the place where physics, imagination, and the hunger for understanding converge, where the silence of the cosmos speaks in wavelengths too faint to hear, but whose message is clear. Keep looking. The hidden universe, illuminating cosmic darkness through hydrogen's whisper. On the afternoon of May 6, 1937, an enormous symbol of engineering pride and technological ambition descended toward its mooring mast in Lakehurst, New Jersey. The German airship Hindenburg, a leviathan of the skies and a marvel of intercontinental air travel, suddenly erupted into flames. The hydrogen that lifted it, a gas prized for its lightness, ignited with terrifying speed, engulfing the vessel in a fiery inferno witnessed by horrified onlookers. Though most on board survived due to the airship's proximity to the ground, the tragedy spelled the end of the hydrogen-fueled airship era. A simple element, hydrogen, composed of one proton and one electron, had unleashed catastrophic energy when given the right mix of air and a spark of ignition. This elemental simplicity is deceptive. Hydrogen is odorless, invisible, and under the right conditions, violently reactive. In the case of the Hindenburg, the combustion of hydrogen ended an age of flight. But the power contained in the atom is not limited to chemical combustion. In nuclear physics, it serves as a gateway to vastly greater energies. The detonation of atomic bombs in Hiroshima and Nagasaki illustrated the terrible potential of fission. But the true apex of destructive energy lies in hydrogen fusion. Thermonuclear weapons based on the fusion of hydrogen nuclei, far more powerful than fission bombs, have only been tested in controlled detonations, never unleashed in war. Ironically, the same scientific curiosity that unlocked the hydrogen bomb also illuminated the stars. Many physicists who developed nuclear weapons were simultaneously probing the processes that power the cosmos, and it was hydrogen again that held the key. Yet while hydrogen's role in stellar fusion and weaponry occupied some minds, a quieter revolution was unfolding within astronomy. The focus of this revolution was not devastation, but discovery. John Oort, a preeminent Dutch astronomer, had already revolutionized our understanding of the Milky Way by showing that the Sun was not its center, but merely a peripheral resident located about 30,000 light-years from the galactic core. His work had confirmed that the Milky Way rotated like a massive spiral, and he became one of the most respected figures in the field. But by the early 1940s, war had disrupted European science. Oort, having protested the Nazi regime's dismissal of his Jewish colleagues, retreated from public academic life. Yet in isolation, he was not idle. The need to understand the true shape and extent of our galaxy continued to stir his scientific instincts. Oort's challenge was formidable. The Milky Way is a dusty system. Optical telescopes, which rely on visible light, are significantly hampered by interstellar dust that absorbs and scatters light. A comprehensive map of our galaxy would require seeing through this veil. The solution, Oort believed, lay in detecting radio waves, which possess much longer wavelengths and are largely unaffected by dust. But for this to work, the interstellar medium, the gas and plasma filling the galaxy, would need to emit radio signals detectable by Earth-based instruments. A breakthrough came in the form of a smuggled issue of the Astrophysical Journal that described potential methods of detecting radio emissions from space, or realized that hydrogen, which made up most of the interstellar medium, might provide the signal he sought. but the emission would need to be both widespread and physically plausible to detect. He tasked his student Hendrik Christoffel van de Hulst with identifying a suitable spectral line from hydrogen-1 that could serve as a beacon in the radio domain. Van de Hulst approached the problem with diligence, exploring the quantum mechanical behaviors of the hydrogen atom. In quantum terms, even the hydrogen atom's simplest structure harbors complexity. While most transitions involve electrons leaping between discrete energy levels, there exist subtler transitions hidden within those levels. One such transition is the hyperfine spin flip transition. In this phenomenon, an electron orbiting a proton changes its spin orientation from parallel to anti-parallel. The energy difference between these two configurations is minute but real. When an electron flips to the lower energy state, it emits a photon with a frequency of precisely 14204 EHz, equivalent to a wavelength of 21 centimeters. This emission lies firmly within the radio band, making it an ideal target for radio astronomy. Van de Hulst published his theoretical prediction in 1944, suggesting that this 21 centimeter hydrogen line could revolutionize our understanding of the Milky Way. The challenge, however, was daunting. The spin flip transition is extraordinarily rare. The spontaneous transition of a single atom may occur only once in several million years. To detect such a faint signal would require immense quantities of hydrogen, far more than anyone had yet confirmed in the galaxy. Skepticism was understandable. Many doubted that the universe held enough neutral hydrogen to make the 21 centimeter line detectable at all. Nevertheless, Oort pressed on. Using salvaged components from wartime German radar equipment, he attempted to build a radio detection system, but he was no electrical engineer and the project stalled. Meanwhile, across the Atlantic, a team at Harvard, led by physicist Edward Purcell, had independently read Van de Hulst's paper and taken a keen interest. Purcell, whose background lay in nuclear magnetic resonance, saw an opportunity to apply his expertise in radio detection. He enlisted his graduate student Harold Doc Ewan, whose knowledge of radar technology proved crucial. Ewan constructed a horn antenna, essentially a hollow metal structure shaped to direct radio waves into a receiver using basic materials, copper-plated plywood, and campus electronics. This antenna, installed through a fourth-floor laboratory window, became the first successful apparatus to detect the elusive 21 centimeter line on a quiet Easter morning in March 1951. The experiment worked. A distinct spectral line at 1420 mmHz was observed, proving the existence of vast hydrogen reservoirs in the Milky Way. News of the success quickly reached Europe, and a collaborative scientific dialogue was born. The Americans shared the technical expertise needed to construct and calibrate radio receivers, while the Dutch provided the astrophysical framework that made sense of the findings. This transatlantic partnership catalyzed the field of radio astronomy, allowing astronomers to build detailed maps of hydrogen distribution throughout the galaxy. More than that, they could now measure not only where the gas was, but also how it was moving. By examining the redshift and blueshift of the 21 centimeter line, astronomers could determine the radial velocities of hydrogen clouds. These observations confirmed that the Milky Way was a rotating spiral with arms that could be traced far beyond the reach of optical light. The implications for galactic astronomy were profound, but the significance of the 21 centimeter line extends far beyond our local spiral. The same principles can be applied on cosmological scales. Hydrogen was the most abundant element produced in the Big Bang, forming the vast majority of normal matter in the early universe. Before galaxies, before stars, before planets, the universe was filled with diffuse clouds of neutral hydrogen gas. Much of this gas still exists today, and the hyperfine transition remains a tracer of its distribution. In particular, the 21 centimeter line offers a window into one of the most enigmatic periods of cosmic history, the cosmic dark ages. After the universe became transparent, following recombination, roughly 380,000 years after the Big Bang, there were no luminous objects to emit visible light. The photons from recombination gradually red-shifted into the microwave regime, becoming the cosmic microwave background. For hundreds of millions of years, the universe remained dark in the optical spectrum, filled with hydrogen gas and dark matter, but devoid of stars. Yet, even during this period, structure was forming. Dark matter, which interacts gravitationally but not electromagnetically, began to collapse into filaments and halos. The baryonic hydrogen gas followed, drawn in by gravity, settling into the gravitational wells created by dark matter. As these gas clouds cooled and contracted, the conditions for star formation began to emerge. But to the human eye or any optical telescope, this process was invisible. The universe was still dark. Herein lies the power of the 21 centimeter line. Unlike light from stars which did not yet exist, the spin-flip transition of hydrogen could still occur. While individually rare, the sheer volume of hydrogen in the early universe ensures that the signal, when observed across cosmic distances, becomes statistically significant. By tuning radio telescopes to the red-shifted 21 centimeter line, astronomers can detect the distribution of hydrogen across different epochs, tracing the evolution of matter long before the first starlight. Modern radio telescopes, such as the Square Kilometer Array under construction, are designed to take advantage of this fact. They aim to create three-dimensional maps of hydrogen distribution, effectively watching the universe evolve from darkness to light. These observations will not only pinpoint the locations where the first stars formed, but also help refine models of cosmic inflation, dark matter behavior, and the initial conditions of structure formation. The 21 centimeter line, then, is more than a spectral signature. It is a cosmic thread linking the present to the past, the luminous to the unseen. Through it, we can observe the quiet gathering of matter during the Dark Ages, when the universe was laying the scaffolding for galaxies, stars, and ultimately life. In retrospect, the hydrogen atom, simple though it may be, has proven to be one of nature's most eloquent storytellers. From the fiery destruction of an airship to the ignition of thermonuclear reactions, from the blazing cores of stars to the near-silent whisper of spin-flip transitions, hydrogen reveals itself across every scale. It is the most ancient of elements forged in the first few minutes of the universe, and it remains our most powerful tool for deciphering the cosmos. And so the universe was never truly dark. It was simply speaking in a different language, one that required new instruments, fresh insight, and a longer wavelength. The 21 centimeter line was the translator, the beacon, the whisper in the silence. Through it, we continued to learn that even in the deepest void there is form. In the darkness there is structure. The hidden universe is not empty. It is waiting to be heard. Let there be light, reconstructing the universe's path out of darkness. The deep ocean, Earth's largest and most enigmatic habitat, provides us with a terrestrial analogy for the cosmic darkness that once enveloped the early universe. As one descends beneath the sunlit surface of the sea, the light diminishes with increasing depth. At just 10 meters, the warm hues, reds, oranges, and yellows are absorbed, rendering the underwater world increasingly blue and green. By 50 meters, much of the visible spectrum has been swallowed by water, and the world is cast in an eerie monochrome. At 200 meters, one enters the twilight zone, a realm populated by bioluminescent creatures that have evolved to generate their own light. By 300 meters, one is immersed in the ocean's true darkness, an environment hostile to human perception yet teeming with life, adapted to this lightless realm. The metaphor is apt, for the early universe too was a place of darkness, not devoid of activity, but veiled from our visible senses. In the cosmic timeline, a similar descent into darkness followed the initial brilliance of the Big Bang. After the universe cooled from its initial hot plasma state and atoms formed during recombination, the cosmos entered a prolonged period of darkness. This era, known as the Cosmic Dark Ages, lasted for hundreds of millions of years. During this time, the universe was devoid of luminous sources, no stars yet shone, and no galaxies yet burned. And yet, like the deep ocean, the darkness was not synonymous with emptiness. Invisible to the human eye and to optical telescopes, the universe was already undergoing gravitational assembly beneath the shroud of blackness. The architecture of structure formation had already been laid. The gravitational influence of dark matter had begun to assemble filaments and halos, forming a vast cosmic web into which neutral hydrogen comprising the bulk of ordinary matter began to accrete by approximately 200 million years after the Big Bang. These dense hydrogen pockets had collapsed under their own weight to the point where fusion could be triggered. In doing so, the first stars ignited, and with them the first starlight broke the cosmic darkness. From every direction across the expanding cosmos, the first sources of light flickered to life. These were likely massive, short-lived population 3 stars, composed almost entirely of hydrogen and helium and devoid of heavier elements. Yet despite their brilliance, these early stars were not immediately able to flood the universe with light. The space between stars remained filled with vast amounts of neutral hydrogen, which readily absorbed specific wavelengths of radiation, particularly in the ultraviolet and optical bands. Much as ocean water absorbs light in the red and blue wavelengths, the surrounding hydrogen gas acted as an opaque veil that muffled the newborn light. An observer at this time might witness stars shining, but with their light dimmed and scattered, their spectra marred by characteristic absorption lines, specifically the Lyman alpha transition, and others where hydrogen absorbs at well-known visible wavelengths. The effect would not have been a total darkness, but a spectral tinting light filtered and shaped by its medium. The appearance of light did not therefore signal an immediate end to the Dark Ages. Rather, it marked the beginning of a new cosmic transformation, the epoch of rionization. During this epoch, the ultraviolet radiation from the first stars and later from the first galaxies began to ionize the neutral hydrogen that pervaded space. To understand this process, it is important to recall the atomic physics of hydrogen. In the Bohr model, the hydrogen atom consists of a proton orbited by an electron. When a photon carrying energy equal to or greater than 136 electron volts interacts with this atom, it can ionize it, freeing the electron from the proton and converting the atom into an ionized plasma. Following the Big Bang, the universe was too hot for neutral atoms to exist, and all matter was in the form of plasma. It was only after cooling for hundreds of thousands of years that electrons and protons combined to form neutral hydrogen, ushering in the Dark Ages. Now, with the advent of the first stars' photons with energies exceeding the ionization threshold began to reverse this process. Each luminous source created a local bubble of ionized hydrogen, a transparent region through which light could travel more freely. Initially, these bubbles were isolated and surrounded by darkness, but over time, as more stars and galaxies formed, the bubbles expanded, began to overlap, and eventually percolated through the intergalactic medium, transforming the universe from opaque to transparent once more. This global reionization of the universe was not the result of individual stars alone. Although population 3 stars contributed to the early phases of reionization, Their short lifespans and limited ionizing output suggest they could not have completed the process alone. Instead, it was the first galaxies harboring longer-lived population 2 stars' massive star-forming regions and potentially active galactic nuclei that provided the sustained ionizing radiation necessary to reionize the cosmos. By about 1 billion years after the Big Bang, the reionization process was largely complete, and the universe became once again transparent to ultraviolet and visible light. Photons could travel across vast distances without being absorbed, and the large-scale structure of the universe could be observed in the way we experience it today. However, the details of this transformation remain elusive. The Dark Ages and the Epoch of Reionization represent a missing chapter in the cosmic narrative. A few galaxies from this time have been observed, dim ancient sources detected at extreme redshifts, but they are sparse to reconstruct a coherent picture of this era. From such a thin sample would be like reconstructing all of human history from a single archaeological artifact found every few centuries. The desire to peer into this mysterious epoch was a primary motivation for the development of the James Webb Space Telescope, launched on December 25, 2021. Whereas the Hubble Space Telescope operates primarily in the optical and near-infrared bands, JWST was designed to probe much further into the infrared. This distinction is critical due to the expansion of the universe. Light from distant galaxies is redshifted, its wavelength stretched such that photons originally emitted in the ultraviolet or optical range arrive at Earth in the infrared. Hubble's instruments, while powerful, are limited in their ability to detect these heavily redshifted signals. JWST, by contrast, can detect galaxies whose light has redshifted entirely out of the visible spectrum. Within its first year of operation, JWST succeeded in detecting some of the most ancient galaxies ever observed, with estimated formation times just 350 million years after the Big Bang. Yet even JWST has limitations. While it can observe further than any previous telescope, its field of view is small and its resolution constrained by its mirror size. Moreover, it is not equipped to see the earliest stages of the Dark Ages or to map the reionization process in its full complexity. To push further to capture the moment when the first hydrogen atoms were reionized, we must turn to an entirely different part of the electromagnetic spectrum, the radio band. As we journey backward in time, observing galaxies at ever greater redshifts, we simultaneously confront a paradox. The farther we look, the more of the universe we see per unit of sky area, but the lower our spatial resolution becomes, individual stars and even individual galaxies vanish into the statistical noise of unresolved light. To see structure on these large scales, we must observe phenomena that are spread broadly across space and time. This is where the 21 centimeter line predicted by Van de Holst and discussed earlier becomes essential. As described, the 21 centimeter hyperfine transition of neutral hydrogen occurs when the spin orientation of the electron and proton in a hydrogen atom change from parallel to anti-parallel. This transition releases a photon in the radio part of the spectrum with a wavelength of 21 centimeters and a frequency of 1420 MHz. Though rare, the immense quantity of neutral hydrogen in the early universe makes this transition statistically significant over cosmic volumes. Critically, the presence or absence of the signal can trace the progress of reionization. In regions where hydrogen remains neutral, the 21 centimeter emission persists, but in ionized regions where electrons and protons no longer form bound atoms, the signal disappears. Thus, during reionization, the universe begins to resemble a cosmic Swiss cheese, with neutral hydrogen representing the solid structure and ionized bubbles representing the holes. By mapping these patterns, astronomers can infer the size, shape, and evolution of the ionizing sources, be they first stars, galaxies, or black holes. The signal offers a three-dimensional view of the invisible universe, providing not only spatial but also temporal information thanks to the redshift dependence of the wavelength. Detecting the 21 centimeter signal from the epoch of Ryanization is one of the most ambitious goals in contemporary astronomy. The challenges are formidable. The signal is faint, so faint that it is overwhelmed by radio noise from our own galaxy, from Earth-based sources, and even from distant quasars. Extracting the 21 centimeter signal requires instruments of unprecedented sensitivity situated in radio quiet zones and equipped with advanced signal processing algorithms. Projects like Hera-Lofar and the upcoming SKA are designed specifically to overcome these challenges. Their success will provide a definitive timeline of Ryanization, reveal the properties of the first light sources, and perhaps even detect primordial black holes. And so the phrase, "let there be light," acquires new meaning in the cosmological context. The universe did not flip a switch from darkness to illumination, rather it transitioned gradually through complex, overlapping processes. Light was born, struggled to escape, and slowly carved paths through the opaque hydrogen fog. The first stars kindled the cosmic dawn, but the light they emitted was absorbed, reprocessed, and shaped by their environment. Only after 1 billion years of growth, radiation, and transformation did the universe become transparent once more. Even now, we are only beginning to uncover the full extent of this transformation. The Dark Ages and the epoch of Ryanization remain a frontier in our understanding, an interval that shaped everything that followed, yet still shrouded in mystery. But with every new instrument, every new signal, we peel back the layers. We listen for hydrogen's whisper in the radio spectrum, decode its interaction with early starlight, and search for the moment when the cosmic night began to fade. And so we ask, is it truly possible to find the signal of Ryanization and illuminate the Dark Ages? The answer lies not only in better telescopes, but in our persistent curiosity. For even in darkness, the universe leaves traces. And when we tune our ears to the right frequencies, we find that the cosmos was never silent. It was always preparing to speak. The signal listening to the universe's silent dawn. Imagine yourself standing under the searing sun in the heart of the Australian outback. All around is a parched and ancient landscape, an expanse of ochre earth punctuated by sparse, withered vegetation. The air shimmers with dry heat. No rivers flow, no clouds break the sky. Yet this land, seemingly inhospitable to humans, sustains other forms of life. Sheep graze quietly. Cattle meander across the dust. They inhabit this terrain differently, not just physiologically, but perceptually. For them, this land is not the red and gold of our human vision, but a landscape shaped by different wavelengths of light, processed by different kinds of eyes. Biological vision systems vary dramatically across the animal kingdom. Humans with our red, green, and blue cone cells perceive the world in a narrow slice of the electromagnetic spectrum, what we call visible light. But this is only a fraction of what exists. Cattle and sheep lack the ability to detect red entirely. Snakes, though color deficient, can sense infrared radiation, a capacity that aids them in tracking warm-blooded prey. Scorpions, astonishingly, can both detect ultraviolet light and fluoresce under its illumination. Nature is filled with such diverse perceptual tools. Unlike any other species, however, humans have transcended our biological limitations by constructing artificial extensions of our senses. In mimicking nature's diversity of perception, we have invented instruments that detect ultraviolet, infrared, X-ray, and critically radio waves. In doing so, we did not simply build new tools of perception, we developed entirely new modes of communication. What began as terrestrial radio, an attempt to broadcast sound and images, quickly became something far more profound. By accident and intention, we began detecting the faint whispers of the universe itself. In the process, a new discipline was born, radio astronomy. By tuning our instruments to the longest wavelengths of the electromagnetic spectrum, we began to detect radiation, not just from other rooms or cities, but from planets, stars, galaxies, and the earliest moments of cosmic history. It was through these technological eyes that humanity found its way into the electromagnetic realm, otherwise inaccessible to biological life. It is deep in the Australian outback, one of the quietest radio environments on Earth, that one of the most consequential developments in the study of the early universe unfolded. Here, far from the noise of cities in the Murchison region of Western Australia. A desert covering nearly 50,000 square kilometers, with only about 100 inhabitants. A seemingly unassuming radio antenna detected something extraordinary. The instrument known as EDGES stands in stark contrast to the massive dishes and gleaming optics we typically associate with astronomy. It is a modest ground-based radio antenna designed to do one thing: detect the red-shifted 21-centimeter signal from neutral hydrogen gas that pervaded the early universe during the cosmic dark ages and the subsequent epoch of rionization. These hydrogen atoms formed after recombination and before the ignition of the first stars emit radiation at a characteristic wavelength of 21 centimeters due to the hyperfine transition of the hydrogen atom's ground state. But as the universe expanded, these photons were stretched, redshifted, so that today they arrive at Earth with wavelengths between 1 and 2 meters, depending on their origin epoch. EDGES was designed to detect these photons not by imaging them as a traditional telescope would, but by measuring their collective brightness. Temperature, a global signal that provides an averaged view of hydrogen gas across cosmic time. It listens passively, its human operators often hundreds or thousands of kilometers away. The experiment operates like a celestial thermometer, scanning across radio frequencies to search for faint spectral dip signatures of interaction between hydrogen and the earliest radiation sources. In 2018, EDGES made a startling announcement. After years of careful calibration, noise modeling, and data analysis, the team reported the detection of an absorption feature at a frequency corresponding to redshift 17, or roughly 180 million years after the Big Bang. This detection, if confirmed, would mark the earliest direct evidence of the first stars, a cosmological milestone tantamount to discovering a birth certificate for stellar light. However, the implications of the signal extended beyond its timing. The depth of the absorption feature was twice as large as predicted by any standard cosmological model. In essence, the signal suggested that the hydrogen gas of the early universe was significantly colder than existing theory allowed. The discrepancy sent shockwaves through the cosmology community. At the heart of the puzzle lay the physics of the 21 centimeter line. The absorption of background photons at this wavelength depends on the spin temperature of hydrogen, which in turn is influenced by the kinetic temperature of the gas and the radiation field present. A deeper absorption trough implies that the hydrogen was either much colder than expected or that the background radiation field was much brighter. Both possibilities were unanticipated. One line of interpretation suggested a radical solution. Perhaps dark matter, long assumed to be non-collisional and thermally inert, could interact, however weakly, with normal baryonic matter. In this hypothesis, collisions between dark matter particles and hydrogen atoms would transfer kinetic energy, cooling the gas beyond standard expectations. If true, This would represent a fundamental shift in our understanding of dark matter with profound implications for particle physics and cosmology. The possibility electrified the field, but scientists proceeded with caution. Extraordinary claims demand extraordinary evidence, and the sensitivity of the EDGE's experiment made it susceptible to contamination from terrestrial and galactic radio noise. The signal detected was incredibly faint, many orders of magnitude weaker than foreground radio emissions from our own Milky Way galaxy. Extracting the desired signal required complex modeling and subtraction techniques. Could the observed dip be a result of unmodeled instrument noise? Was there an unrecognized astrophysical foreground? Was it an artifact of calibration? To verify the result, independent confirmation was essential. A range of follow-up experiments soon emerged. In India, the SARAS experiment placed an antenna on a floating platform in a lake to minimize ground reflections and environmental noise. Its analysis, however, failed to reproduce the deep absorption feature reported by EDGES. While SARAS did not conclusively disprove the detection, its inability to corroborate it cast doubt. The field, always driven by data, began to retreat from the more exotic interpretations. The initial theories invoking dark matter-hydrogen interaction gave way once again to methodological scrutiny. Perhaps the signal was a systematic artifact, or perhaps the models of galactic foregrounds were insufficient. The return to conservatism was not defeat, it was scientific self-correction. And yet the potential insight gleaned from even the possibility of the EDGE's result had already reshaped priorities in observational cosmology. Despite the controversy, EDGES had achieved something critical. It had galvanized the global scientific community to take the 21 centimeter cosmological signal seriously. Across the Murchison outback, other instruments were already listening. The Murchison Wide Field Array, comprised of hundreds of bow-tie-shaped antennas, had been probing the structure of the early universe through interferometric imaging, searching not for global signals, but for spatial fluctuations in the 21 centimeter line caused by the patchy nature of ionization. The local indigenous Wajari Yamaji people, stewards of the land, have poetically described the MWA as the ear that listens to the sky. Now, the Murchison site is preparing for the most ambitious project in the history of radio astronomy, the Square Kilometer Array. When complete, the SKA will consist of over 130,000 antennas distributed across the Australian desert. It will have the sensitivity to detect an airport radar from 10 light years away, and will be capable of mapping the epoch of ionization and the tail end of the cosmic dark ages with unprecedented resolution. And yet even the quiet Murchison region is not immune to interference. Human radio transmissions, satellite communication, and atmospheric disturbances continue to challenge ultra-sensitive observations. The ultimate destination for uncontaminated cosmology may lie beyond Earth entirely. Plans are already underway to deploy radio antennas on the far side of the Moon, a location naturally shielded from Earth's radio noise. There, in the permanent radio silence beneath the lunar regolith, astronomers hope to finally detect the primordial signal in its purest form. The pursuit is not merely technical, it is philosophical. The universe was dark for nearly 200 million years, not because nothing was happening, but because our instruments and senses were not attuned to its language. To optical eyes, the early cosmos appears blank, devoid of structure or meaning. But to a properly tuned antenna, the sky becomes alive with history. The 21 centimeter line, faint, elusive, and ancient, carries with it the tale of hydrogen clouds, cooling, collapsing, and forming the first stars. It chronicles the transition from plasma to atoms, from darkness to light, from silence to symphony. The EDGES experiment, despite its debated result, opened a new chapter in our exploration of the universe's earliest epochs. It reminded us that even in apparent silence, the universe has a voice. And now, with every new generation of radio instrument, we are learning how to listen more carefully. The Dark Ages were never truly dark, not to the sky itself, nor to the photons that have traveled billions of years to reach us. They were simply waiting for the right kind of eye.